Alright, time for another draftphysics.com, debatephysics.com also. But again, the debate is impossible. Nobody reasonable will show up to have the debate, so I have to have an unreasonable debate with nonsense. So first I'll read a comment by the channel 321 guy, and then we'll deal with Ian Gosling again explaining, what he believes, not doing a fake experiment for a change, but just doing a fake premised diagram, you could call it, I suppose. Illustration, I don't know. Yeah, I don't know. Pantomime. He's doing pantomime. Anyway, so I said the second compression wasn't any more difficult than the first compression. So the simple argument is what Hooke's law is basically saying is, said you could take a spring, and let's say it just read in pounds or something, and I held it down at 1 pound. So it's only 2 pound scale, right? So this is what's left. This is as much work as this was. It's not a different amount of work. All you're going to get is the same thing out. So it doesn't matter where I lock the scale. If I put an impulse in here, okay, the impulse will technically do the same amount of work on the scale, all right, within the tolerances of the spring. So Hooke's law falls apart once you maximize how much compression the spring can take. Then it becomes harder and harder to compress it any further. And of course you'll get less back from it also. All right. So yes, that's the response. And now another thing here is this apple and orange argument about the difference between impulse energy and a constant application of energy. So there's a difference between constantly applying a force, and not. Yeah. A constant force where it's constantly held in a position, and an impulse force that only happens for you collect the energy and then it's give back time. So unless you do something to mechanically register what took place isn't going to last too long, because the energy has a limitation. It's only a certain amount for a certain amount of time. All right. So it does make things a little more difficult, because in gravity, out of gravity, you can have subtly different expectations for what's going to happen. I don't think they're dramatically different, but anyway. So I don't know. I have to keep illustrating this. I don't know. Is there any point? But let's do it one more time. So if you're just dropping a 1 mass on a scale, all right, it acquires for a falling distance. I would argue 1 centimeter is all you need. Okay, you drop it 1 centimeter, it will weigh on the scale, all right, twice its mass weight. Okay, so if you just let it sit on the scale, it's going to register an amount, a 1 on the scale. And if you drop it 1 centimeter, it'll read a 2 on the scale. All right, and if you drop it from 4 centimeters, then it'll read a 3 on the scale. Okay, so 4 centimeters will get you this, 1 centimeter will get you this, and no centimeters will get you that. Let's see, I just want to make sure I double. This could be a 4 here, I'm not sure which one. When I'm doubling the mass, this is a 4. Okay, all right. No, it isn't. Yeah, I just have to think. 4 times the height is twice the weight. Yeah, of what you're weighing. This weight. So yeah, it would be a 4. All right. Anyway, let's say this is there's elements here that can make it something simple confusing, and it's just not that confusing. So the simple argument is you get 1 unit of scale compression per item you drop. And so if I drop a second item, right, then it's the second unit. The third item is the third. And it doesn't matter whether I drop them individually, I'll get like say 3 impulse units, I'll get 3 times the scale will move this much distance. And if I drop all 3 at once, then I'll get 3 units of distance. Okay, that's all I'm going to get. It's the same amount of energy, whether they're individually dropped or whether they dropped all at once. It's the same amount of energy, and it's just weight. Weight is momentum. That's the simple argument. And so your weight in gravity is a momentum, and the momentum is that you're going to go 1 mile an hour. So if I take the scale and I weigh you, and then I turn the scale sideways, okay, so now it's going to push you. It's going to push you at 1 mile per hour, no matter how much you weighed. So if you were an elephant, you're going to leave with 1 mile an hour. If you're a mouse, you're going to leave at 1 mile an hour. All right, because the weight it registered is essentially, okay, a momentum, and your velocity is the same because gravity gives you the same velocity regardless of your mass, and the only thing that's changing is your mass. And so obviously the amount of energy you stored in the spring is exactly the energy you put into the spring. So gravity is putting into the spring 1 mile per hour at your mass. That's the sitting on the scale energy. So while you're sitting on a scale, basically your momentum is 1 mile an hour times your mass. All right, so I mean, it's really, I just don't know where they're going. I mean, they keep defending some notion that this is quadratic, that it isn't this obviously Hooke's law kind of proportion, and that somehow secretly I can drop a 3 mass in some special way and end up getting 9 units of energy back out, and I can't. Okay, so I'll play the half of his video where I just stopped listening. This is, I stopped playing it. Is it just, how can you keep defending something you have no evidence for it? You can't explain it. You just keep saying it. Right, so instead of drawing it, he's just sliding pieces of metal on this board and saying this is what it takes. So even though there's no evidence that it takes more energy or any of that, he's just going to say it. So yeah, he first starts off fine. Okay, 1 unit of energy, 1 mass. Then you add a second mass, you have a second unit of energy, a constant force being applied. Okay, because it was in gravity. All right, they don't move by themselves with any kind of magical energy. You have to give them energy going in, and gravity constantly pushes where a velocity doesn't constantly push. So in most cases, unless you're using something that has an accelerating pedal or it has some way to apply a constant force, we're talking about an impulse. All right. And you should make those distinctions. But of course he doesn't, and the result is nonsense.
Do that as it does to do that.
So he's saying that's the same, I'm saying that's the same energy. Why would I be saying that? That's not what I said. And again, if you apply the impulse energy all at once, then it's 3 units of energy you're using to do this. Obviously, you can't do it with 1 unit of energy. There's no way 1 unit of energy can do 3 units of energies of work. So I don't even understand your point. 3 bullets has more energy than 1 bullet. I've never denied that is absolutely true. I mean, if I shoot 3 bullets, I'm going to get more atoms displaced than if I shoot 1 bullet. I mean, duh. So, where are you going with this argument? There's nowhere where I even implied that doing this one motion is the same as pushing the rubber band 3 units of distance. Of course it's not, because the other 2 masses are applying the extra 2 units of force. I mean, it's just ridiculous. Now just go from this to this line, and the argument is that yes, as long as these 2 masses are doing the work, as long as they're on the scale, then yeah, the one mass can finish the job.
You do, don't you? You do. 3 times the force. One times the force. 2 times the force.
Right, exactly. So 1 times the force, 2 times the force is twice the motion, twice the compression of the spring. So 1 unit of force added plus another unit of force, they both do the same work, and it's demonstrated by Hooke's law that they do the same motion in the spring.
3 times the force. So therefore it's only 3 times energy. It's not though, is it? No.
So he's still going to contend that somehow I can put 3 units of energy in and get 9 units of energy out. We know that, look, if the spring, if I compress this, right, a distance, and then we know we have stored a certain amount of energy. And so let's just say the released energy is it moves a mouse 1 mile an hour. That's how much energy this is. A mouse goes 1 mile an hour. All right, if I put the energy in, I put 2 units of energy in, I know it's only 2 equal masses that create that in gravity. We know gravity does the same thing to both objects, so if I put 2 mice on here, I got the 2 mice amount of energy. Well, then if I remove one of the mice and turn it sideways, well, then I can expect the mouse to leave at 2 miles an hour, because now I have the compression of 2 mice and I'm only shooting 1 mouse. Oh, fuck.
How can that energy, how can that be the same as that energy?
So again, it's not. Obviously, the 2 things are already moving. So yes, it's 3 units of energy. All 3 of them are moving. One of them isn't pushing all 3. All 3 of them have motion still in that direction. You're saying they don't have that anymore. Well, then put 1 here and say, okay, I've stopped the spring here. Now the spring's compressed this much with a constant force. And now you're going to compress it again. And then you're going to stop this, you're going to put a lock on it, and now you're going to hit it with 1 unit more of energy. Well, do that, but don't do this nonsense.
I mean, in a way, do I need to sort of go into any more detail?
Oh, fuck. You know, this is just so ridiculous. You're making a preposterous claim, okay? 10 times the force, 100 times the energy out. I put 10 in, I get 100 out. That's your silly theory. I put 5 in, I get 25 out. Again, we're back to spinning motors and all this other crap. It's a ludicrous proposition, okay? It doesn't fucking happen. It doesn't take 25 times the energy to spin a motor 5 times as fast. It's just not a fact. It's not anywhere close to a fact. It's as far away from a fact as you can fucking get. It takes 5 times the energy to go spin a motor 5 times as fast. It even takes less because there's less friction, frankly. So this is just bullshit. You're arguing absolute nonsense and pretending, just fucking pretending. Oh, anybody's got to be able to figure out that, yes, 3 units of energy is 9 units of energy. Of course it is. No, of course it isn't. What you put in is what you get out. Shit. You put 3 1 masses in. Okay, that's it. Whatever motion they had, whatever momentum they had, you have to conserve, you fucking idiot.
No, because immediately anybody, any normal person, they immediately sees the fallacy of what you're saying.
Oh, where do they see it? I don't. How do I? This is absolute nonsense. You're going to compare dropping a 3 mass to dropping a 1 mass, and you're going to claim somehow I'm saying those are the same things. No, of course they're not the same thing. And they're 3 constant force masses. So again, do it with an impulse. Yes, 1 impulse, 1 mass impulse. I get a dent in the spring. The spring springs back up again because I dropped it from some height. It weighed more than its rest mass. From a centimeter, it's double. That's not saying that, oh yeah, that's the same thing as dropping a 3 mass once. No, it's not the same thing. 3 mass is different. It's 3 times the energy. 3, not 9 times, 3.
It must require more energy to move that much force. 3 times the force.
So it's that much force to move that much force. So you can't even get the vernacular even close to right. Ugh.
Through the same distance as 1 times the force through the same distance.
So again, he keeps claiming it's true, but he doesn't have any evidence that it's true. And the scale is basically telling you it's not true. Hooke's law is telling you it's not true. All I have to do is double the force, and I've doubled the compression. So I just double the mass. I put 1 mass on, 1 unit. I put a second mass on, leaving the first one on, 2 units. There isn't 3 units of energy in this and only 1 unit of energy in this. Which one had the 3 units of energy? Magical energy. No, it's just 2 units of force being applied by gravity. Gave the same force to this one as it gives to the other one. They both have the same amount of energy to push on the scale. And the scale is saying the force needed to push this much is the same as the force needed to push this much. In terms of just adding it. And so 2 units of compression will only get you 2 units of force out. Fuck. This guy can't, it's, this is so flat earth crazy. This idiot can argue this as if he's got some evidence somewhere, and he has none. No car crash analysis, no anything, no bowler testifying to, wow, how much more power I got with that 8-pound ball going twice as fast. Yeah, I knocked down so many more pins. No, nothing. No wrecking ball guy saying, gee, why am I using this big heavy wrecking ball? It seems like such a waste of energy. When I should be just shooting bullets at the building and knocking it down.
There must be an increase in the energy required. Harry.
Oh, fuck you. Don't call me by my name, you retard. You're not behaving like any kind of civilized being. I mean, how can you be this grotesquely and insanely arrogant to say, oh, it's quite obvious, Gary said, 1 mass does the same work as 3 masses. No, it's not what Gary said, retard.
Surely you can see that.
Oh, fuck you. Alright, just so bad. It's just so dismal. I don't even want to look. I hate this shit, this fucking YouTube bullshit that it won't let me watch videos. Except, when you're not signed in, they do this fucking autoplay and you can't get rid of it. It's so annoying. I mean, if you just open one video in one private window, you're just stuck with it being the default. Fuck. I'll pause and see if I have the courage to face another moronic disbar video. Probably not. No new disbar video, so good. Maybe he's out of the let's do fake experiments business. Maybe he's finally finding a better some better way to do dishonor to the human race. Anyway, but it's such a simple experiment, right? So he did one version of it that was almost credible. So you have you're just going to use this lever, a stick, okay? And you have to account for the fact that the stick has a mass, right? The lever always you have to account for the fact it's not an idealization. It's always going to add some weight to your experiment. That is, it's going to absorb some energy, and it's going to have some energy when it's moving. And so what you want is the mass of this lever to be much less than the weights, 10 times or greater a difference between the weight. So for all you want to do is a simple experiment, right? You want to drop a 1 mass, right, from 4 units of distance high, all right? not on some arc, just 4 units of distance high versus 1 unit of distance for a 4 mass. Okay, 4 mass, something 4 times as heavy. So you just want to be able to make something here that's 4 times as heavy and has the same center of mass. And so you just want to, in the 4 mass case, have the mass the same distance, swinging on the same arc. Then you can use these numbers. If you swing them on different arcs, or you do something else to change where the center of mass is, then obviously you can't do the experiment that way. But it's a simple enough experiment to demonstrate that, 1 mass, okay, dropped 4 units of distance, that is going twice the velocity, is not the same energy, okay, as a 4 mass, all right, dropped at 1 velocity, okay. Obviously this is more momentum. So momentum does matter. You can't have more momentum and the same amount of energy. It doesn't make any sense. It's nonsense. 2 things with different amounts of momentum can't have the same energy. They can't knock down the same number of pins. I mean, we can go back to 2 years ago in this bowling analogy. I mean, I went through the whole analysis, right, of just showing what happens. What do you think happens? Can you diagram for me what happens when the 8-pound ball going twice the velocity hits the first pin it hits? What happens to that pin? And when the 16-pound ball going half the velocity, just 1V, what happens when it hits a pin? All right, and I went through the whole thing and explained. I gotta remember which way this goes. Sorry. That obviously, the first pin, all right, getting hit by the higher velocity, it will absorb more energy from the bowling ball. The 8-pound ball will give the first pin more energy. Okay, almost twice as much. It'll give it twice the velocity, almost twice the velocity. So if it was a velocity of, say, 10, okay, and we know the ball will lose the momentum for each pin it hits. All right, so you just multiply the 10 velocity times the weight of the pin, 2 or whatever, 20, and then we know the 16-pound ball going to the much slower speed, the pin will leave at a slower velocity. It can't go the faster velocity than the ball has. So we know it's stuck going the 1 velocity, the 5 in this case, let's just say. And so its total is going to be, 10, where the other one's 20, kind of thing, right? Or 5. So yeah, it's got 1 velocity. And this one's 10. And so we know the pin is going to fly off with more momentum, twice the momentum, this first pin. But what's happening when you get down to the last pin? Well, the last pin, the 16-pound ball, okay, is the one that's still rolling and still has momentum, and the 8-pound ball has almost nothing left. So it'll be the 16-pound ball that'll be giving the much greater amount of energy, because it's going to retain more of its velocity because it lost less of it per pin. Per pin it hit before it got to its last pin, it gave each pin less velocity. The curves go, I went through all this. I mean, how can it's undisputable. This is what's going to happen, right? The 8-pound ball is going to give away the energy like this. All right, and the 16-pound ball, okay, is going to give the energy away. How to draw this right? Yeah, it's right. Okay, 16, okay, is going to give the energy away in this manner. Okay, kind of thing. So the 8-pound ball gives away a lot of energy early, but it doesn't have any staying power. And the 16-pound ball gives away less energy. I guess the chart should be something like this, actually. So yeah, the 2 lines are going to cross is the point. So, and how exactly they look when they cross. So there's going to be just as much area under here as there will be under here. It's just that the area is going to have a different shape. But there's going to be just as much total energy because they both have the same momentum. They have the same capacity to move matter. They'll just move it differently because of their different velocity. One will give away more energy quickly, and one of them will have more energy over a longer period of time. So we're back to, right, 1,000 atoms moving 1 mile an hour versus one atom moving 1,000 miles an hour. Obviously, the one atom moving 1,000 miles an hour is going to give away a lot of energy very quickly. And the one going, the 1,000 atoms going 1 mile an hour are going to give away the same amount of energy just over a larger period of time, because each one of those interactions will take longer because it's a lower velocity. It takes longer to hand somebody 1,000 $1 bills than it takes to hand somebody a $1,000 bill. So it's the time component. And so time does matter, but it doesn't make something have more energy. The fact that it gives away its energy more quickly doesn't mean it has more energy. It just means it will have a different effect on something. So, you can tap a glass 170 times like that and nothing breaks. But if I take all of that tapping energy and hit it once, it breaks. Doesn't mean that the one hit had more energy. It just means that you distributed it beyond the tolerance of the substance you're hitting. The substance couldn't absorb the energy that quickly. It needs to absorb it slowly and over a period of time. So you can make this argument with heat. You could apply a lot of heat over a longer period of time, or a little bit of heat over a short period of time. And the point is if the little bit is too high a heat that it can't be absorbed by the object, then the object will break. But if you slowly heat it, it doesn't break. I mean, there's so many arguments. But anyway, it's just so bad. These people are just so, to sit there and just keep claiming it's so well established when I've gone through the history. They have no experimental evidence. The experiments that were done in the 1700s were garbage. Denting clay with round objects. I mean, they're garbage experiments. The axioms were never proven. Right now, we still don't have any explicit evidence that, 4 pounds with one velocity is the same energy as 1 pound with 2 velocities. Absolutely zero evidence demonstrating that's a fact. And they just keep doing this arrogant nonsense of saying, why don't you believe in our religion? Haven't we proven it by drawing you with a picture of Jesus walking on the water? Isn't that enough? Here's a little paper cutout of Jesus, and I'll have him, move across the paper on the water. Isn't that good enough? No, that's not good enough. All right, anyway, just so bad. I mean, not to admit that these questions are open questions at minimum, and I would argue that just you're adding up the pieces. The fact that there is no evidence is evidence against. Okay, when something can't be shown or demonstrated, it's likely because it's not true. All right, so I'm just looking around. So I guess that's it. Anyway, I just continue to hate this planet. Just hate the bugs roaming it, thinking they're using intelligence somewhere. Pathetic.